Characterization of a recombinant vector using restriction enzymes. Restriction enzymes recognize short DNA sequences and cleave double-stranded DNA at the specific within or adjacent to the sequences. Approximately 3,000 restriction enzymes recognizing over 230 different DNA sequences have been discovered. There are 4 types of restriction enzymes. Type 1 restriction enzymes were originally thought to be rare. Nowadays, from the analysis of sequenced genomes, we know they are common. These enzymes are considered as multifunctional proteins with both restriction and metallase. Therefore, they are a combination of restriction and modification enzymes. They cut DNA at random far from their recognition sequences and require both ATP and S-adenosyl L-methionine to function. They are considerable by chemical interest, but they have little practical value since they do not produce discrete restriction fragments or distinct gel binding patterns. Rather than forming a single family of related proteins, type 2 enzymes are a collection of unrelated proteins of many different sorts. They differ completely in amino acid sequences from one another, and indeed, from every other known protein, that they exemplify the class of rapidly evolving proteins that are often indicative of involvement in host-parasite interactions. They are considered as single-function restriction enzymes, independent of metallase. Therefore, they cut DNA at defined positions close to or within their recognition sequences. Most of them require magnesium, and they produce discrete restriction fragments and distinct gel binding patterns, and they are the only class used in the laboratory for routine DNA analysis and gene cloning. Type 3 enzymes are a large combination of restriction and modification enzymes. They cleave outside their recognition sequences and require 2 as cleave at sites of short distance from the recognition site. Furthermore, they require ATP, but they do not hydrolyze it. S-adenosyl L-methionine stimulates the reaction but is not required. Exists as a part of a complex with a modification of the metallase, such as sequences in which opposite directions within the same DNA molecule to accomplish cleavage. It is important to mention that they rarely give complete digest. Type 4 enzymes recognize modified DNA, typically methylated, and are exemplified by the MCR, BC, and MRR systems of E. coli. Restriction mapping using bioinformatic tools for verifying the orientation of the ZF gene inserted on the PCR topo 2.1. The primers used to amplify the ZFY gene, where the forward is the first one that appears and the reverse. We go to the Primer Blast online software, where you can copy and paste the sequence of the forward primer and the reverse primer. It's important to mention that you have to use the reverse complementary of the primer in the reverse case. We use the standard parameters of the page and we click on Get Primers. You have to wait until the server gives us a result, and for this exercise we choose the first one, the first result, which is from the transcript variant 5. Then you go to the NCBI database, you copy and paste the coding sequence that you will use to insert on the vector. This is the vector without the insert, in which we put the regions. In the middle we will insert the PCR product. Here we use the nav cutter, in which we copy and paste the topo vector, and we choose a circular visualization. Then we go to the custom digest menu and choose the enzymes we want to cut the vector in order to verify the orientation. There were chosen the ECHO R5 and SCA1. Then you click on digest, and if you want to view the gel, how it will be visualize experimentation and you get an idea, you click on view the gel, and then you can choose the percentage of agarose and load a 1 kilobase ladder for visualizing the length of the bands. Then for the clockwise direction, you insert the PCR product you get from the primer blast and then this coding sequence. You copy and paste it in the clockwise direction and then you paste it on the NetCutter online version. You also click on circular visualization and go to the custom digest option. Then you choose Echo R5 and SCA5. So here you go to Echo R5 and SK1. Then you click on the green button on the bottom and digest, and you got your map. Also you can use the gel. As I said, click on the agarose percentage and the ladder. And for the counterclockwise direction, you have to put the insert, but put it also on the NetCutter. Go to custom digest, choose the enzymes you want to use, Echo R5 and SK1, then click on digest, and you got this map. You also can visualize the gel, and that's all. There are some considerations when using restriction enzymes experimentally: the temperature and condition, the buffer composition, the influence of DNA methylation, digestion with multiple enzymes, restriction, recognition sites and requirements, and the start activity.
Gel electrophoresis for verifying the orientation of CFY gene insert on PCR topo 2.1 vector, 1% agarose gel, only 1 kilobase marker, only 2 blue colony plasmid without digestion, 3 blue colony plasmid with code SCA1, 4 blue colony plasmid code with ECOR5, 5 blue colony plasmid code with SCA1 and ECOR5, 6 white colony plasmid without digestion, 7 white colony plasmid code with SCI1, 8 white colony plasmid code with ECOR5, 9 1 white colony plasmid code with SIC1 and ECOR5. The following characterization yield show the plasmid PCR topo 2.1. In all wells, there was contamination with proteins. In the well 3, 7, and 9 is completely degraded sample, which was cut with the SCA1 enzyme, while in the well 4 and 8 show 2 bands that are cut sample with ACOR5. In the well 5, cutting is not only shown as a band shown, this sample was cut with both enzymes.
When performing a digestion with restriction enzymes, it is often a good idea to choose 2 different enzymes that will give you unique but different patterns so that you get a better confirmation that the insert was correctly cut. June 2016. It is important to take into account that one must follow established protocols for the enzymes to use so that this won't have star activity and make sure somehow that they will perform what we expect. Also, a purified DNA sample free from salts or organic compounds, it is 100% important to take into consideration when performing a digestion, because these contaminants may affect the enzyme activity and so the whole experiment.
To carry out enzyme reaction protocols must take many considerations and precautions. This to get the desired cuts. First, it's necessary that the quality of DNA sample is completely pure, without contamination of organic dissolvents to avoid knockout cuts. It's also essential to respect the concentration of reagents, such as glycerol and amount of enzyme. This is to avoid the star activity that the original non-specific cuts. It is necessary to respect the temperature, reaction time, and buffer used to have the expected results.